Neutrons are fascinating. They are tiny particles found inside atoms. Atoms make up everything around us. But here's the puzzle. Neutrons are unstable on their own. If you take a neutron out of an atom, it will quickly decay. This decay happens in about 15 minutes. The neutron transforms into other particles, a proton, an electron, and a nearly undetectable neutrino. This seems strange. If neutrons are so unstable, why are they everywhere? The answer lies within the heart of atoms. Inside the nucleus, neutrons are surrounded by protons. A powerful force holds them together. We call it the strong nuclear force. So, while a lone neutron is fleeting inside an atom, it helps build a stable and lasting structure. This balance of instability and essential presence makes neutrons truly remarkable. Let's dive deeper into neutron decay. Imagine a seesaw. On one side we have the neutron. On the other side we have a proton, an electron, and a neutrino. The weak nuclear force controls this seesaw. It's one of the four fundamental forces in the universe. When a neutron decays, the weak force causes it to transform. It's like the seesaw tipping. This process has a specific time frame. We call it the half-life. The half-life of a neutron is about 15 minutes. This means that in 15 minutes, half of a group of free neutrons will decay. Understanding neutron decay helps us grasp the fundamental forces shaping our universe. It's a reminder that even at the tiniest level, change is a constant. Inside an atom's nucleus, things get crowded. Protons with their positive charges should repel each other, yet they stick together. How? This is where the strong nuclear force comes in. This force is incredibly powerful, the strongest force we know. It acts like superglue, binding protons and neutrons together. Think of it as a powerful attraction that overcomes the proton's repulsion. This binding energy is essential for the existence of atoms as we know them. Without it, the universe would be a very different place. No stable elements, no stars, no planets, and certainly no us. The strong force ensures that neutrons, though unstable alone, become vital components of a stable whole. This stability allows atoms to exist, and from atoms, everything else follows. From the Big Bang's fury, the birth of neutrons, let's rewind the cosmic clock to the very beginning, the Big Bang. In the first moments of the universe, everything was incredibly hot and dense. It was a chaotic soup of energy and particles. As the universe expanded and cooled, this energy began to condense. Protons and neutrons, the building blocks of atoms, started to form. Imagine the universe as a giant cooling oven, baking these fundamental particles. The early universe was a neutron-rich environment. Free neutrons decayed, but new ones were also constantly created. This constant interplay between creation and decay shaped the early universe's composition. This early abundance of neutrons was crucial for the formation of the first elements, setting the stage for the universe we see today. Stellar forges, where neutrons build the universe. Stars are the cosmic kitchens where heavier elements are cooked. Deep within their cores, intense heat and pressure allow for nuclear fusion to occur. This process fuses lighter elements into heavier ones. Neutrons play a critical role in this stellar alchemy. They act as building blocks, adding to the nuclei of lighter elements. This process, called neutron capture, creates elements heavier than iron, like gold and platinum. Imagine stars as giant recycling centers. They take the basic ingredients, hydrogen and helium, and through a chain of nuclear reactions, create a stunning diversity of elements. These heavier elements are then dispersed throughout the universe when stars explode as supernovas. This cosmic dust eventually forms new stars, planets, and even life itself.